Welcome to your lesson on areas between curves. And have you ever noticed that Ireland is just a one sea away from Iceland? So there's an area between those two curves. Okay, to begin our discussion area between curves, we should quickly recap finding area under a curve. So the process we followed there was to place a series of rectangles under the curve under which we want to find the area. And by finding the sum of the areas of those rectangles, we can approximate the area under that curve. For example, here, rectangle 3, to find the area we had base times height, and the base was 0.5. When you subtract those two numbers, you get a distance of 0.5, and the height is found by putting an x value into the function, so 1 goes into the function f of x, which produces this y value, which essentially is the height of that rectangle. So we have our base and height, we can find the area. And then we take the sum of the areas of all the rectangles, in this case 4 rectangles, so you can see we have n equals 1 to 4, that will produce areas of 4 rectangles. And if we take that sum, we have an area under the curve. Of course, it's not perfect, and the more rectangles we create, the closer we are to approximating that area. So if you take that process to further, we can have many rectangles, and writing it as a general rule, we have this rule here. So we're finding the sum of all the rectangles, and the rectangles are represented by these. So this idea has turned into this. This change in xi is the change in x values from here to here, and that change represents again the base of the rectangle. And here we have that x value put into the function, which again, just like here, we saw when we input the x value into the function, we get the height because we get the y value. So here's our height, here's our base, that's the area of one rectangle, and then we're going to do the sum of all the rectangles. So that's how we find the area under a curve. That, as I described in our recent lesson, turns into this and this, because basically we don't want a limited number of rectangles, because there will always be a small gap unaccounted for. So what we do is we assign a limit to that sum, saying that we want that width of those rectangles to approach 0. So we're going to make that width, or the base of the rectangles, become so tiny it essentially becomes 0. In other words, we are creating infinite rectangles there, and that will give the best approximation of the area. When we apply a limit to a sum like that, through the work of calculus, that becomes an integral. So an integral essentially is the infinite sum of rectangles there. And that's what the word integration means. It means to take infinite small parts, integrate them, means put them together into something. And that's what integration is doing. It is taking infinite small rectangles, putting them together, and finding that area. So that is our integral, and that's where it comes from. So the integral from a to b is from some starting point to end point. And then these are rectangles, right? So again, this is our width of a rectangle, and this is our height of each rectangle. Okay, so that's area under a curve, and now we're going to look at area between curves. So here we go. We have here now, instead of just one curve like we had here, we have a green curve and a pink curve. Two functions graphed on this coordinate axis, and we are looking for the area in between the purple zone. In this case, we can say we have a bunch of small rectangles here, more rectangles here, and more here. The problem is sometimes the green curve is above the pink one, and sometimes the pink one is above the green one. So to deal with that, let's talk about that. Well, first of all, what's the height of one of the rectangles here? If you look at that height is now not just the f of x, like before the height was just the function, right? Because it gives us the height of from the axis to the curve. But now the height is not one of the functions, it's actually the two subtracted, because we need to do green function minus pink one, and then we get the height, right? Because if we just did f of x, the green function, we would have the height all the way from the axis to there. And if we did g of x, the pink function, we would have the height from the axis to there. So if we subtract those two heights, we get the height of one of the rectangles. So that's kind of the step we take forward when we do area between curves. So in this case, in this little rectangle, you can see the f of x or y value here is 5.28, and the f of x or y value here is 3.33. If we subtract those, we will actually have the height of that rectangle. How about here? What are you going to do to find the height here? Well, in this case, we have to do g of x, the pink function, minus the green one, because now the pink one is on top. So it's that value we have to use to subtract the other value. If you did that, you would notice that one has a y value of, or g of x, a y value of 1, and this one's negative 2.05. But when you do negative negative here, you're going to add those, and you'll get a height of 3.05. And that makes sense for that height there. So sometimes we're going to subtract f of x minus g of x, sometimes g of x minus f of x. So just to recap all that, here was our area under a curve. I changed the f of x to a y, just using simpler language, so the height is the y value, and this is the width. So now in the integral for area between curves, it looks like this. The idea of subtracting those is what we just talked about. My question to you is, what does this represent? Okay, yeah, that was the width of one of the rectangles, which means the base of the rectangle. And what does this represent? Okay, that represents the height of each of the rectangles when you subtract the two functions. And what does all of this represent? Okay, all of that is base times height, so it's the area of one of the rectangles. And finally, when you do this, what does that represent? Well, that now takes, sorry, let me go back. This now takes all these rectangles, so the infinite number of rectangles, and puts a sum on all those areas. So that's where the integral formula comes from. Let's go on to a problem here. So we have, considering the area between these two curves, so we have this parabola, x squared minus 2x minus 1, and we have this line, half x minus 7. And we're trying to find the area from negative 0.75 to 1.75. And you can see here, negative 0.75 and 1.75. First question, what would you use in this case? Would you do f of x minus g of x, or g of x minus f of x? Okay, we would use f of x minus g of x. We always do the upper curve minus the lower one. And maybe this question was asked because sometimes we assume, since both curves are in negative y values here, you might be thinking I'm going to take the one that's lower minus this one. But no matter where the curves lie, you always do upper one minus lower one. Okay, so f of x minus g of x. Okay, so going through that process, we can see we're going to do rectangle by rectangle. We're going to do this piece by piece like we did before. So here's our first rectangle, and that goes from negative 0.75 to negative 0.25 here. So that's the width. That's our width. We can find that by doing that difference there. And then the height of that rectangle. Again, we're going to subtract the two functions with the x value put in, right? So we're taking an x value of 0.5, which is the mid value here, because you can see the curve passes through all the mid values of the rectangles. So 0.5, negative 0.5 put into there, negative 0.5 put into there, gives us our two y values. And when you subtract those, you get the height of that rectangle, right? The two y values subtract to give you the height. So now we have the width and the height of that rectangle. We can multiply those to find the area. If we continue that process, we can find the area doing all 5 rectangles. So we continue on, and I repeated that process here for the next 1, 2, 3 rectangles. Finding their width. The width is all the same for them. Finding their height by subtracting f minus g, and then multiplying to find the area. So we're getting a total area here so far. Please try that for the last row here. What will the numbers be? Okay, so there's the last rectangle. This orange one, the width is the same. The height can be found by putting 1.5 into the f function, 1.5 into the g function. Subtracting those, we get a height of 4.5. Multiplying the width and the height to get this area right here. Finding the sum of all those, let's see. So the estimated area would be this number here. We summed all those areas, we get this number, so that's an approximation of the area between the curves, right there, from there to there. Let's see how close that is by actually using integration. So what would be the definite integral for finding this area? Based on all I've talked about so far here, what do you think? What would be the definite integral we would set up to find this area? Well, here we have it, alright. So again, it's top function minus bottom function to find that height of the rectangles. Here's the width of the rectangles expressed as d of x, change in x. And here is the boundaries we have from negative 0.75 to 1.75. Okay, so you know how to do integration. If you do integration on this, we should be able to find the area. But first, we should simplify that. So we can combine these here. I subtracted half x, and I added 7. Now find the integral of that, or the antiderivative. So the antiderivative is this, and now our bounds of integration are here. We're going to substitute these in and do a subtraction, right? So 1.75 is substituted in, minus, and then 0.75 substituted in. Long calculation, final answer on our calculator. So we can write that out. You can do all this on your calculator, but you also know how to run an integral on your calculator. So maybe running this integral will be easier. And we get an area of 13.8. Wow, that's incredibly close to our approximated area, which was 13.75. So those rectangles were a very good approximate representation, because you can see there's not much that they go above and below. They're a very good approximation. That was great. Okay, so now let's find, this is a summary of what we've talked about. So pause and take a look at this in the video right now. Okay, now that you've paused and read that, let me move over to the next slide. Let's try this problem. This says it's a calculator problem. Okay, how do we begin? Well, this one is a calculator problem, so the expectation is you graph it. So I have a graph of the two curves here. We can say for, oh, and notice here, it didn't give us boundaries. It just said find the area between these curves, like bounded by these two curves. So that means it says like you need to find out where the boundaries are, like where do they cross each other, because those are the endpoints. And then once you know those endpoints, you can say I'm going to find that area. So finding those endpoints, you can use your calculator, right? We know how to graph two curves and then find the intercepts by doing second calc and then finding the intercepts. So we can have the intercepts right here and here, and calculated we find them to be this point and this point here. If you don't have your calculator, you can use Desmos and do the same thing, find those intersection points. So now we know the boundaries of that area, are these two numbers. So now run an integral on that to find out the area. Try it now. Okay, so the integral looks like this. We're going to do upper curve minus lower curve to find the height of the rectangles. There's our boundaries. Put that integral in your calculator. Also, Desmos does this also, so you can put this in Desmos and see what you get in case you don't have your calculator. Okay, so, oh wait, well, I have the answer right here, so there's your answer there. Hopefully you got the same one to match that. Okay, next question is a non-calculator question. Notice it has the same thing. We're finding the area bounded by these two curves. So again, we need to graph both of these and then figure out where they intersect, because those will be the boundaries of that area. So this one, notice the curves are simpler than the last one. So that's why this is a non-calculator question. You're expected to be able to graph these by hand. This is a line and this is a simple parabola. So try to graph those. Okay, well, let's say we didn't graph them yet. I just have a rough drawing here. This is not the drawing for these because these are two parabolas. But again, we're looking for this area and we're looking for the intersection. So what are those 2 points where these two would intersect? You can do that by setting them equal to each other and then solving that equation. So again, non-calculator, so you should be able to do this by hand. So I set them equal to each other, and then I notice I have a quadratic. I moved everything to one side. I have 0 here. I factored that to get this, and that allowed me to solve for two x values, -1 and 2. And since I started by saying when is this equation equal to this one, my answer represents those 2 points. So for our situation, those 2 points are -2 and 1. That's where they intersect. So those are our boundaries. But if you still don't have a graph, you don't know between those two boundaries, is this one the top curve or is this one the top curve? Because we need to know which one's on top. So to do that, I took a point between the boundaries, between -2 and 1, and I chose the point 0, and I plugged it into both equations. And when I plug in both equations, it tells me which one has a bigger y value, which in essence is telling me which one is the function that is on top. So I found out that the parabola has a higher y value, so it is on top. So when I set up my integral, I put that one on top right here, and I subtract the other one. Okay, now running the integral, check your work there. There's the graph. If you want to see how your graph looks, confirm everything, we can see the parabolas on top, we can see that area, and the area is this value here. One last one, try this out. calculator and check your work.